recording notification.
Now it's recording.
There we go. Okay, perfect. Hey, welcome everybody to Friday afternoon session. We're going to be covering CPU profiling on expense. And let me just paste this into the chat one more time for the folks who are just joining. So I put together a few simple examples along with my slide deck, and they're all available at the following GitHub repo. So if you want to go there, maybe follow along with the slides there in case you're having a hard time following in real time. You want to be able to refer back to something I said earlier. So just a small correction to the title. So I'm not going to cover MPIP today. I'm going to restrict this to Gproff and MuProf. And also when it comes to UProf, we don't have it installed for general use yet on Expanse. It will be coming soon. So you'll be able to run the UProf examples at that time. I'll say though that I did save the output from UProf. So if you want to take either the plain text CSV output and paste it into a spreadsheet, or if you have a Windows or Linux machine at home, you can install the UProf GUI so that you can ingest the database. I'm not demonstrating that because we don't have the GUI installed on Expanse, and I have a Mac, and AMD does not currently have a GUI for interrogating the UProf output. So I'm going to go ahead and share my screen. And Mary,
yes.
How long do I have?
You have 2 hours.
Okay.
You have till 3 o'clock. So, and if you want to go to 5, I'm okay with that.
I was actually thinking of going shorter because okay. I don't think anybody wants to be here for 2 hours on a Friday afternoon, and I might have to duck out a little before 3 anyway.
That's fine, Bob. You have plenty of time.
Okay, so everybody here, you're seeing my slides now, right?
Yes.
And I'm not in any kind of weird presenter mode with timers or anything on the side.
Nope.
Alrighty, perfect. And then finally, this is a pretty small group. We can keep things relatively informal. I'm happy to take questions at any time as we go along. And I'm going to ask, maybe Mary and Jeff, if you can keep an eye on the chat, because it's hard for me to have an eye on everything. I'll check it every now and then, but if you see a really good question come through, feel free to interrupt me, and I'll try to answer it.
Okay. Sounds good.
All right, so we're going to be talking today about CPU profiling on Expanse, and we're going to be looking at 2 tools, Gproff and UProf. So before we dive into actually using the tools, we want to ask ourselves, why do you want to profile your code? And I see 2 reasons you want to do this. First of all, you want to determine what portions of your code are using the most time. So if you're experimenting, say, with small codes, toy codes, things that you're putting together for a single purpose, you might find that your software base is pretty small. It might be tens to hundreds of lines. But most modern HPC and data-intensive software is thousands of lines. And in fact, I know some packages that are millions of lines. There's a climate code maintained and developed by NCAR called CESM, which is actually millions of lines. So if you're running that code, you're trying to figure out how to make it run fast. So you don't want to just jump in and work your way through all that code. You want to profile it to figure out where the code is spending most of the time. And often you find that it's just a few routines that account for most of the usage. So basically, before you start trying to improve the performance of your code, you need to know where to spend your effort. And then when we get into UProf, the AMD profiling tool, we're going to go a step further, and we're going to try to figure out why those portions of the code are taking so much time. So I find that step 1, just knowing which routines, often gives me all the information that I need. I can say, okay, it's this particular function or subroutine. I'll look at it, assuming that it's well written, that it's not too long. Sticking to usual software engineering standards that a function or subroutine shouldn't be more than 100 lines or so. You can usually tell where the time is being spent. Your eyes should automatically be drawn toward, say nested loops where there's a lot of work going on. But sometimes you might run into a mystery for why that chunk of code is so expensive. And we're going to be showing an example later where you see some vastly different runtimes for slightly different input parameters. So this is where the second element comes in, figuring out why those portions of your code take so much time. And you can get some really valuable insights if we start diving into the performance counters. And this is something that Uprof will give us that Gproff can't. So Gproff is a really, really old tool. I mean, this is amazing. It goes all the way back to 1982, and it's still the first tool that most folks go to when they need to profile their code. When you think in terms of technology, not 1982 might as well be centuries ago. I like to give the examples of technology of the time. We had a supercomputer, a Cray XMP, which had a peak performance of a little under 1 gigaflop. So if you could take your cell phone, your present day cell phone, and go back to the mid 80s, you would be a supercomputer center. Or you look at cell phones of the day, where they're these giant bricks. They were, they weighed a few pounds. They had a big antenna sticking out of the top, and they cost about $4,000. So the fact that we have a profiling tool that goes back to that era, that's almost 40 years old, but is still so valuable, is amazing. Another great thing about Gproff is that it is non-proprietary. It's not tied to any specific vendor or any specific architecture. As far as I can tell, it's available everywhere, and there's universal support by all major C, C++, and Fortran compilers. In fact, I have never come across a C or Fortran compiler that didn't provide support for Gproff. I know across Intel, GNU, the AOCC, AMD Optimizing Compiler Collection, which is built on LLVM. So if you've ever heard of Clang or Flang compilers, they support it. PatScale, PGI, so pretty much universal support. It's also very, very easy to use. There are just 3 steps, and we're going to be showing this pretty soon. Compile your code with the -pg flag, so that adds instrumentation to your code. Run the code, and it's going to generate a file called gmon.out. And then you just run gproff a.out, gmon.out, or whatever the name of your executable was in place of a.out. And it also introduces virtually no overhead. Now, I should add that Gproff is not what we call a tracing tool. So if you're working with a parallel code and you want to know where time is being spent in communications, if you're looking at things like load imbalance, we've got one more person coming in the room, load imbalance or other factors, you're not going to be able to get that from Gproff. Gproff just tells you about the performance of your underlying serial code. You can use Gproff with parallel codes. What you end up doing is getting one gmon.out file for each MPI process. So it might be numbered, labeled gmon.0.out, gmon.1.out, and so on. So it's going to be on a process by process basis. But again, it's not going to capture communications overhead. So there are other tools like Tau, which are ideal for doing tracing. I already mentioned Gproff introduces virtually no overhead. There are some tools that are very heavyweight that might be able to give you more information. And what they try to do is subtract out the overhead that's introduced by the profiling process. But in Gproff, you won't need to do that. And let me just go back to the chat one more time. I see we had a couple of folks who came in late. So I'm just going to post this again. So for those of you who came in since I started, I put together a GitHub repo with a couple of examples, some output from the AMD Gproff tool, and a PDF of my slide deck. Okay, so Gproff is going to give you two types of output, what we call the flat profile and the call tree. Flat profile is going to appear at the top. And it's very simple. It's just a listing of the functions and the subroutines ordered by their relative usage. And if you're lucky, you're going to find that it's just a small number of routines that account for the large majority of the runtime. So you can see this is going to be very useful for identifying the hotspots in your code. So in this case, I'm showing the Gproff output from a real life code. This was from a collaboration that I had with the J. Craig Venter Institute, or JCVI. They're just off of campus over near the theater district. I was collaborating with a biomedical research group that specializes in a technique called flow cytometry. So this is used to characterize cell populations. So cells will be tagged with fluorescent antibodies that bind to different cell markers. Very, very heavily used, say in immunology for classifying populations of B cells and T cells. The number of markers can vary. It's anything from 6 up to, in some of the newer technologies, close to 100. So the problem is that with the data that we get, we have this high dimensional data where we're measuring fluorescence in anywhere from 6 to 100 different dimensions, and we're trying to take that data and cluster them to recognize different cell populations. So it's a very computationally difficult problem. So I got a hold of their code. I started profiling it, and we can see here, starting from the top, we have a routine called get number packed data. You can see in the first column, per percent time. So that is the percentage of the time that is spent by that routine. The next two columns are going to be cumulative seconds and self seconds. So cumulative, you can see that it's growing as we go down our list. So this is a running total of all of the time spent by all of the routines up to that point in the list. And then the other column, self seconds, is the time actually spent by that routine. That's followed by calls. That's the number of times that routine was called. And then the time per call, milliseconds per call, and then the total. So you can see that get number packed data accounts for 68% of the usage, main for 13%, quick sort double for 11%, and then a few other routines. So this is really nice. This is what we like to see when we profile a code. That it's just a handful of routines that account for nearly all of the runtime. There was an application that I had profiled a few years ago, which was the exact opposite of this, where the usage was spread out pretty evenly across 30 or 40 different routines, each of which were taking 2 to 3%. So that would have been a really tough task. But in this case, we know immediately to zero in on get number packed data. Okay, the other output they're going to get from Gproff is the call graph. And this gives you additional levels of detail, such as the exclusive time spent in a function, the time spent in all children, functions that are called by that function, and then statistics on calls from the parent. So we're going to start at the top here. We're going to see that the first routine in this list is main. Now, if we go back to the previous slide, we see that main was actually number 2, that it consumed 13% of the time. But in this case, we're seeing the functions ordered by their by self plus child usage. So this is accounting for all of the routines that are called by main. So you'll see in the first column, time, 96.9% is in main. That should really be 100%, but there's always going to be a little bit of variation when we do the profiling. The next two columns, self and children, give us the amount of time spent directly in main, and then children is in the functions that are called by main. Then you'll see 5 lines following main for get number packed data, is hump, quick sort, radix sort flock, and ID2 center all. Along with the time that's spent in each of them. For example, we see that is hump accounted for 123 seconds of usage. In the next column, called, this gives you a breakdown of how many times the routine was called and how many times it was called by main. So in this case, main is the only function that actually calls is hump. So is hump is called 22,183 times, and all of those were by main. Above that, we see get number packed data. There's about 399,000 calls. And again, all of those calls were by main. We go down to the next entry, and this is get number packed data. And you'll see that main is indented and it appears above get number packed data. So now that we're focusing on get number packed data, we're seeing the time that's actually spent in that routine, and we're seeing the routines above it that call it. And if there were any routines that it calls below it, they'd be listed. And we see that in the next entry for is hump. In this case, is hump is called by main, and it in turn calls get nearest events, pack arrays, and pack points. So when you're profiling codes, I want to just point out it's really important as you go through the process of optimizing your application that you reprofile. So you might find that what was originally a hotspot, after you've worked on the code, after you've optimized performance, is actually much faster and new hotspots are going to emerge. So in this case, this was after one round of optimization. We could see that get number packed data has now moved down to the number 2 spot. It only counts for 26% of the time, whereas previously it was 68% of the wall time. Main has moved up to the top. Previously, it was only using 13%, but now that we've made get number packed data so much faster, main is actually accounting for 41% of the time. And this is one of those applications where I actually went through a few rounds of optimization and profiling. Eventually, we were able to get it to run, I think, about 10 times faster than the original version. But again, if I had stopped, or sorry, if I hadn't reprofiled after that first round and that second round, I wouldn't have known, say, to focus on these other routines. So we're going to look at a simple Gproff example, and this is kind of contrived. It's a code that doesn't really do anything, a small Fortran code with a main program that calls 2 subroutines. They call them sub1 and sub2, and then sub1 calls 2 functions, f1 and f2, and it calls each of those functions n times, and then sub2 is going to call f2. Sorry, is only going to call. Oops, sorry, I got my labeling backwards. It says sub2 is going to call f2 n times. So to do our profiling, really simple. I'm going to build my code. The only thing that's going to be different is I'm going to add that -pg flag so that I insert instrumentation into my code. I'm going to run the code. In this case, I'm using the Linux timer time just to see what the overall wall clock time will be for the application. And then when it's time to do the profiling, I do Gproff followed by the name of the executable, in this case, intro, gmon.out, and I'm going to redirect that into a file where I capture the profiling. Okay, so in my simple Gproff example, I ran this, and it was really, really interesting. The first time that I did this, the runtime reported by Gproff showed that 100% of the time is attributed to the main program, and we see absolutely no usage data for sub1, sub2, f1, or f2. So again, going back to my example, given that I used an input value of 1 billion, which means I'm going to be calling one of these functions 2 billion times and the other one 1 billion. Sorry. Yeah, well, one of them sorry, it's going to be, well, one of them 3 billion times and the other one 2 billion times. You would expect that most of the usage was going to be there. But instead, we found that all the usage was was in the main routine. So anybody who hasn't looked ahead in the slide deck, do you have any idea what might have happened here? Any guesses? Okay, so I see something here in the chat. Okay, so a couple of comments. Eric said no idea. -03 optimized the calls away. Yes, in a sense, it did do that. So Dario, do you want to did you want to expand on that at all? Yep, exactly. And inlining. So I will get to that in the next slide. So perfect. So what happened was sorry, who was the commenter there? That was Dario. That's exactly what happened. So this is one of the first lessons I think you could take away here, is that an optimizing compiler may make transformations to your code that render it unrecognizable. So there's a compiler optimization called function inlining, which takes the body of a function and it moves it into the routine that had called it. So this gives you a couple of advantages. First of all, you avoid the call overhead, and it also enables further optimization. Since once the body of the function is moved into the calling routine. So in fact, you're going to find that 2 levels of inlining were performed. So remember that main is calling sub1 and sub2. Sub1 and sub2 in turn are calling f1 and f2, which just operate on an element of our array. So if we look at the block of code, you know, where these routines are called, we have 2 calls to sub1, 1 call to sub2. Those calls are actually replaced with the body of routines sub1 and sub2, which were loops do I equals 1 to n, or we assign the output of functions f1 and f2 for on element xi, yi to zi. And then the second call was with the arguments rearranged, and then sub2 just calls function f1. So what I did was I went back and I decided, let's profile it again, but this time with function inlining explicitly disabled. This is something that you normally wouldn't want to do. I did this just for illustration purposes. But with the Intel compiler, there's a flag where you can set the inline level. Here I set -inline -level equal to 0. So now when I profile the code, it looks a lot more like what I had expected. So if I look at the flat profile, which is going to be at the top of the Gproff output, you'll see that I spent 39% of the time in function f1, 26% of the time in function f2, to 20% in sub1 and 7% in sub2. Now sub1 and sub2, they really don't do very much. All they are is a wrapper to repeated calls to functions f1 and f2. But what you're seeing here is that there's a significant amount of function call overhead. And that's why these routines actually have a pretty significant usage. If I look down in the call graph, and I didn't reproduce the whole call graph here, I'm just showing a small fragment of it. And I realize that my indentation is a little off, and I'll fix that in the slides a little bit later. That sub1 is called by main, it's called twice. And then it calls f1 and f2. And notice here that we have, for f1, we'll see 2 billion / 3 billion. That means that sub1 called function f1 2 billion times, But in total, F1 is called 3 billion times. The other 1 billion was from the calls from sub 2. And then for function 2, it's only called by sub 1. So all 2 billion of the calls were from that routine. Okay, another lesson to take away from Gproff. We found that there was one small quirk after we turned off inlining. And that's that the time reported for the entire program using the Linux time utility was about 65 seconds. But this doesn't match what we see in the Gproff output. If we look at the cumulative time, by the time we get down to all of the routines that account for any significant amount of usage, it only comes out to about 26 seconds. So I'm thinking that Gproff probably did a reasonably good job of reporting where the time was spent. But if you really want to get accurate timings, then there's no substitute for measuring directly. And you can do this at the level of the entire program, like I did with the Linux time utility, or by inserting instrumentation into your own code. And by instrumentation, it's nothing more complicated than putting timers into code sections, say where you're calling the system clock before and after a call to a routine, doing the calculation, the difference and outputting results. And in fact, a lot of production software does that already. It's very, very common, say in computational chemistry and molecular dynamics applications, that in the output, that it will give you a breakdown of how much time was spent in different steps, say constructing matrices or doing matrix diagonalization. So do we have any questions so far? Okay, let's see, again, a few more people came in a little late. I'm posting one more time the link to the GitHub repo, where I have a copy of the slides and also the examples that I used in this tutorial. So again, any questions before I move on? Okay. I want to add that Gproff really doesn't add much overhead. So here I show the run times with different compiler options. So with and without PG, where again PG adds the instrumentation needed by Gproff, and with inlining enabled, inlining disabled. We see that when inlining was enabled, that there was no difference in the runtime. In both cases, it was 18 seconds. When inlining was disabled, I saw that compiling with the -PG flag actually resulted in slightly slower code. In this case, it was about 5%. And this was reproducible. I ran this multiple times and consistently got 65 seconds with -PG, 62 seconds without -PG, which is about the most overhead that I've ever seen Gproff introduce. And my hunch is that this is related to the large number of function calls, 3 billion for this test problem. As I mentioned, this was really a toy code that I put together just to illustrate function inlining and a few of the features of Gproff. And most well-written code will not be calling functions billions of times over the course of running. Okay, so now I'm going to switch gear. We're going to talk about a more modern profiling tool. This is something called Uproff. Sometimes it's also written as Muproff. This is a proprietary tool for profiling, and it only works on AMD hardware. So this is an AMD profiling tool. You won't be able to use it on say, a system with Intel processors. Here, you're going to want to compile your code with the -G flag to get symbol information. It turns out that Uproff actually works pretty well without the G flag. But if you want to be able to tie usage, say, to particular lines in the code, or roughly to lines in the code, you do need to compile with -G so that you get all the symbol information. Profiling data is available in 2 formats. It's output both as CSV files, so these are human readable, and they can be opened in spreadsheets, and also The profiling output is written into a SQLite database, which can then be imported into the AMD Uprof GUI. So in addition to time-based profiling, which is essentially what Gproff is doing, it's giving you a breakdown of time spent in each function or routine, it can also access performance counters to investigate cache usage, branch prediction, and something got cut off there. I think it was also in instruction usage. So the Uprof workflow, it's pretty similar to Gproff. You're going to have a collect phase where you run the application program and collect the profile data. Translate, which is where you take that profile data, you aggregate it and correlate it and save it into the database or into the CSV file. So the translate stage is analogous to when we ran Gproff on the executable and the gmon.out file. And then finally analyze. This is where you view and analyze performance data so that you can identify bottlenecks in your code. So to collect the data, you're going to use the AMD Uprof CLI-bin tool, so the CLI for a command line interface. This is going to collect command where, so this is going to collect sampling using different predefined profiles. I'm going to show these on the next few slides. So usage shown in the middle here is AMD Uprof CLI-bin collect --config, followed by the sampling profile -o output, so that you can specify the root name for the CSV and the root file for the profiling data, and then your executable. So this is going to generate an output.caperf file if you're running on Linux, or an output.prd file if you're working on Windows. So Uprof gives you a lot of control over the information that you want to collect, that you want to sample. The simplest is time-based sampling, TBP, and you're going to use this configuration to identify where programs are spending their time. And again, this is going to be pretty much the same as what you did with Gproff. And then there's a bunch of other predefined profiles, assess_ext, branch, so that you can look into branching behavior, data access, NST access, memory, IBS, assess, and so on. So these predefined profiles, they're really a convenience. So that you don't need to get into the details of all the program counter events that are tracked. You'll see for the second predefined profile, assess_ext, that it lists a whole bunch of events with hex codes, PMCX 076, 0C0, 0C2, and so on. If you go to the AMD Uprof user guide, it defines all of these. So you can specify in particular which events you want to track. But I think in most cases, it's easier just to use these predefined profiles. It's much simpler. So, and counters that would kind of logically go together for profiling your code are already pre-grouped for you. Now, there's one wrinkle that we ran into, though. And then this has to do with something called the paranoid level. So this is a feature of relatively new Linux distributions. So the type of profiling that you're allowed to do is going to depend on the Linux perf event paranoid setting. Where a higher setting means that you're being more paranoid about security. A lower setting, say 0 or negative value, means that you're relaxing it. So as I was experimenting with Uprof, I found that in order to use some of the predefined profiles, we had to go to a paranoid setting that was unacceptably low in terms of security risks. So I won't get into the details here, but if you're interested, here are a couple of links that you could follow that discuss what the paranoid settings mean and what the security risks are. So what we've decided is that when we do make Gproff universally available to users, a value of 1 for the paranoid setting is a nice balance between security and usability. So this allows us to do the time-based profiling and the data access-based profiling that I'm going to be showing in the next few slides. It's not going to allow you to do, say, the branch profiling, where you can investigate poorly predicted branches in your code. But I tinkered with that a little bit, and I found that I could still get that information if instead of using one of the predefined settings, I just manually specify a few of the events that I want to track. So we go back here again to branch. What was it? 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so there were 8 different events that I needed to track, and that was over the limit that was allowed for a paranoid level of 1. Okay, so after we've collected the data, we're going to go into the translate phase. Again, we use the same tool, AMD Uprof CLI-bin, and in this case, instead of collect, we're going to specify report -I followed by the profile data file that I'm going to translate. So this is going to generate a new directory named output, and it's going to contain 2 files, output.csv and output.db. So the former is plain text, while the latter is a database file that could be read by the AMD GUI. And then finally, analyze. Your profiling data can be analyzed anywhere. So what would have been my preferred way of doing this would be to install the AMD Uprof GUI on my local machine, copy over the database and work there. But unfortunately, AMD does not currently have an implementation for Mac. If your personal machine happens to be Linux or Windows, you'll be in luck. You could grab the database files that are in my repo, and you could actually play around with the GUI. I see a comment here in the chat. Okay, thanks, Mary. Okay, so for now, I was just pasting the output into Excel, and I find that this works pretty well, although it requires a little formatting, say column resizing, and familiarizing yourself with the output. But whereas the GUI, it'll make it easier to zero in on just the data that you want, do some sorting, so some nice graphics and displays. So now we're going to go back. We're going to look at the same code again, except this time we're going to be using Uprof for our time-based profiling. When we build the code, it's going to be just the same as before. We're going to get rid of the -PG flag, since that's specific to Gprof. We're going to make sure that we compile with -G so that we get the symbol data. So our build is going to look pretty much the same. And I'm explicitly showing here the inline level flag. I have it in brackets because that is optional. So if you want your code, if you want the compiler to do the inlining, just omit that. If you want to disable inlining, you can include. All right, then we have the collect phase, again calling AMD Uprof CLI-bin, collect --config, in this case TBP for time-based profiling, -O intro-tbp. That means that I'm going to be capturing capturing the output in a file called intro-tbp.caperf, and then finally we're going to execute the code /intro, and then with an n value of 1 billion, and then finally the translate stage, where again running the AMD Uprof CLI bin, this time report instead of collect -I intro, and this is going to point to the CAPR file that I generated previously. So when we look at what's going on with doing the profiling with inlining, it's pretty much what we expect. No surprises here, because the no surprises here because the inlining was done. We've seen this already with Gproff. On the left-hand side, we're looking at a section called hot functions. Main accounted for 14.287 seconds, pretty much the full time. On the right, I'm doing a dive into main. And here we're going to see that there was that Gproff actually tried to assign the time to individual lines of the source code. Now take this with a grain of salt because your optimizing compiler is doing a lot of modifications to code. In this case, for example, you're actually seeing the you're seeing line numbers that would correspond to the inlined code. And we find that just about 5 seconds is spent on the function f1, about 7 seconds on the function f2. We see that a little bit of the time is associated with the do loop, do I equals 1 to n. We would expect that to be pretty much close to 0, and then time scattered across other source code lines. So again, take this with a little bit of a grain of salt. And we'll show an example where this breaks down a little bit more when we disable inlining. Okay, so here's the case. Again, running again. This time we disabled inline. Kind of looks like what we saw from Gproff, but there was one important exception. In this case, the amount of time assigned to the routines is actually very close to the wall clock time. We noticed before that there was a disconnect between the results from Gproff and the Linux time utility, but in this case they actually match up pretty well. You can see on the left in the hot function section that f1 and f2 account for the large majority of the time. 32 seconds for f1, 18 seconds for f2. We have about 5 seconds spent in sub 1. About 1 second spent in sub 2. So this would be accounting for function call overhead. On the right side, we look at a few of the specific functions. And here again, Gproff tried to assign time to individual lines of source code. You'll see for the function f1 that 7 seconds were assigned to the line where we're doing the actual operations, the square roots and divisions. But then the majority of the time was assigned to end function f1. So this is the statement that defines the end of the function. So again, might be some useful information here, but if you're compiling your code with optimization turned on, say -002 or -03, you are going to see some assignments that look not quite right. Okay. Do we have any questions so far? Nothing. Okay. In that case, I will move on. So we're gonna next show how we can use Gproff for data access profiling. But before we do that, I want to do a little bit of digression and get into the computer memory hierarchy and cache. So again, although Gproff can tell you which functions are taking the most time, it doesn't give you insight into why a particular function is so expensive. So especially when we're working with codes that have a low computational intensity. By this, we mean that it performs relatively little computation for each word of data that is operated upon. The performance is going to depend very critically on how well we manage data movement, and in particular, how well we make use of cache. So Gproff gives us access to program counters and lets us go deeper. So a little bit about compute bound versus memory bound codes. Already touching this, in a memory-bound code, it's the rate at which data can be delivered to the CPU. That's the limiting factor. And our goal is going to be to apply cache-level optimization so that the CPU is not starved for data. And then in compute-bound codes, the performance of the processor is a limiting factor. The data can't be delivered fast enough. The data can be delivered fast enough, but the processor can't keep up. And in this case, our goal is going to be to reduce the amount of computation done on a given piece of data. So if we go back and we look at these functions, F1 and F2, this is a case where it really is going to be a compute-bound code, assuming that we're not able to do the inlining. The square root and the division operations are fairly expensive. So we are reading in a value for X, a value for Y, and we are doing a lot of computing on it. So a little bit about computer memory hierarchy. This is you'll see some version of this in just about every textbook on computer hardware. At the top of the pyramid, we have the CPU registers. At the bottom, we have external storage, like say spinning disks and SSDs. The capacity for the registers, it's very, very small. I believe it's under 100 registers in modern processors. So this is where data is held that's available that could immediately be operated upon by the CPU in the next clock cycle. So the latency for accessing that data, it's less than nanoseconds. So on a 3 gigahertz processor, 0.3 nanoseconds later, you'll be ready to operate on that data. So it's very, very fast, but of course the capacity is small. L1 cache you can think of it as a temporary storage on the processor that's close to the CPU. So rather than going out to main memory all the time, we can take data, we can stage it in cache, where it can be accessed much more quickly. Once data is in L1 cache, you could typically access it on the order of a few nanoseconds. And the size of the L1 cache, it's going to vary from chip to chip, but it's typically around 10 kilobytes. We also have multiple levels of cache. There's an L2 and an L3 cache. L2 is typically around 100 kilobytes. Access time is a little bit longer, and L3 cache is usually in the order of megabytes and a little bit further away from the CPU. Finally, we go out to main memory, and access times on the order of hundreds of nanoseconds. But of course, main memory is much larger. On Expanse, the compute nodes have 256 gigabytes of DRAM. And then finally, we go out to disk, where we may have, say in the case of the supercomputer center, petabytes of storage. But that's going to take you often hundreds of microseconds to access that data. So we really want to try not to go out to disk, do what they call out-of-core computing, and try to go out to DRAM as little as possible. Whoops, sorry, wrong direction. Oh no, sorry. So if we want to optimize our code for cache, there are two things that we need to keep in mind: temporal locality and spatial locality. So, principle of temporal locality is that data that was recently accessed is likely to be used again in the near future. So to take advantage of temporal locality, once data is loaded into cache, it's generally going to remain there until it has to be purged in order to make room for new data. For example, if we're working on a data set that occupies a gigabyte, but our L1 cache is only 10 kilobytes, obviously we can't fit that entire gigabyte in there. We can load in some of the data, but then as we need to operate on more elements of our arrays, we're going to have to push data out of that L1 cache, similarly out of the L2 and the L3 caches. So there are some, a variety of cache management strategies that are used, but typically it's going to be some variation of what we call least recently used. So data that in cache that hasn't been touched for a while is going to be preferentially pushed out. There's also the principle of spatial locality, And that's that if a piece of data is accessed, it's likely that neighboring data elements in memory are also going to be needed. So to take advantage of spatial locality, cache is organized into lines. I say here typically 64 bytes. In fact, I cannot think of any processor that uses cache lines of anything other than 64 bytes. Maybe there's some specialized hardware out there, but general purpose hardware, it's always going to be 64 bytes. And the entire line is loaded at once. So our goal in cache level optimization is going to be to exploit the principles of temporal and spatial locality so that we can minimize data access times. So I touched on this already, that main memory is much larger than the cache, and we need a policy for mapping memory locations to cache lines. So this is done in a predictable way. I'm not going to go into the details. If you are a computer scientist or in computer engineering, you'll probably spend an entire semester learning about all of the details of cache and the different types of mappings and algorithms for replacement. But the thing to know is that the mapping between main memory and cache is done in a very predictable way. It will take the first so many bits of the memory address and use that to determine where that data would reside in cache. Okay, so if we're working with one-dimensional arrays, it's going to be very easy to make good use of cache. So 1D arrays are stored as blocks of contiguous data in memory. So here's an example, a little snippet of C code, where I'm allocating an array of 100 integers. So assuming that these integers each take 4 bytes, in memory, I'm going to see that element x0, say, is going to have an offset of 0. x1 is going to be offset 4 bytes from x0, x2 8 bytes, x3 12 bytes, and so on and so on. So cache optimization for 1D arrays is going to be straightforward, and you're probably going to write optimal code without even trying. So whenever possible, just access the array elements in order. So in this case, let's say I wanted to increment each of the elements of x by 100. I would do for I equals 0 to n, x of I plus equals 100. So what's our code doing with regards to cache? So again, assuming 64-byte cache lines and 4-byte integers, when we begin the calculations, the cache is going to be empty. So we're going to load elements 0 through 15 into the cache. We're going to step through those elements and increment each of them. Increment x0, increment x1 through x15. Then we get to element 16. That's not going to be in cache. So what's going to happen is those next 64 bytes are going to be loaded into cache, and it will operate on elements 16 through 31, increment, and so on. In reality, processes are really clever. They will recognize the pattern of data access and prefetch the next cache line before it's actually needed. One question that comes up is, do I have control over cache? And there are no programming constructs that I'm aware of in higher level languages, or even in assembly, that give you direct control over the cache. For example, load a particular location in memory into cache. Modern processors, they directly implement advanced cache replacement strategies, branch prediction, and prefetch mechanisms. You really don't have control over that. I'm going to say the best you can do is try to follow standard practices to exploit temporal and spatial locality, and in some instances, choose optimal parameters based on the cache sizes. Multi-dimensional arrays is where things get a little complicated. So from the computer's point of view, there is no such thing as a two-dimensional array. This is what we call syntactic sugar. It's purely a convenience to the programmer. If you ever look at some really, really old code, even when they're working in multi-dimensional, working with what's essentially multi-dimensional arrays, they'll write it out as a single one-dimensional array and do the indexing, the striding for in the second and third dimensions manually. But under the hood, it's going to be stored as a linear block of data. And this is done in two ways. There's column major order and row major order. In column major order, the first or the leftmost index varies the fastest. And this is a convention used in Fortran, R, and MATLAB. So let's say I have a 4x4 array loaded with these with values 0 through 15. If I'm working in Fortran, the way this is going to be laid out in memory is I'm going to go down the first column, then down the second, then down the third, then down the fourth. So if I look in memory, I'm going to see 0, 4, 8, 12, 1, 5, 9, 13, and so on. Row major order, the last or the rightmost index varies the fastest. And this is the convention used in Python, Mathematica, C, C++, and other C-like languages. So here we're going to go across the rows, 0, 1, 2, 3, second row, 4, 5, 6, 7, and so on. And this is going to have really important implications for writing optimal code. So let's say that we have two-dimensional arrays that we want to add. We're going to do our loop nesting. We're going to flip the loop nesting depending on whether we're working in Fortran or in C. So on the top, I show a block of properly written Fortran code. So in this case, I have do j, do I, and then zij equals xij plus yij. So you see that the leftmost index is varying the fastest. Properly written C code, the rightmost index is going to vary the fastest. Note that I've flipped the loop nesting. I have 4i on the outside, 4j on the inside, then zij equals xij plus yij. So when I say properly or improperly, you can get the loop nesting wrong, and you're still going to get the right answer, but it's going to be very slow.
Yeah, Bob, somebody just asked about the performance and if there was any difference.
Yes, and actually there is a tremendous difference in performance. And we're going to see this in the next one. Oh, and they asked row-wise or column-wise. No. So if you would write the equivalent code in C or in Fortran, and you're aware of the proper convention. So for example, if I took if I executed this block of Fortran code or this block of C code, the timings would be identical. That they would be translated into the same assembly language, and I would see the same performance. But on that point, though, if you get it wrong, it's going to be very slow, as we'll see in our next example. Yep, good, great question. So I coded up the matrix addition problem. It's in the repo. So I measured the runtime for the addition of two large n by n matrices, and I saw some expected behavior and some very puzzling behavior. So this is where I'm adding matrices of size n by n, where n is equal to 32,767, 768, and 769. So first of all, we notice that when we use the proper loop nesting, we're always much faster than the improper loop nesting. So for the first case, 32,767, we can see that our code is about 15 times faster. For the case 32,769 at the bottom of the table, it's about 10 times faster. And for 32,768, it's about 60 times faster. So as expected, the difference in the problem size, it's really not that, it's really insignificant. We can see that the runtimes when we use the proper loop nesting are all about the same, to within a little bit of run variation, but they're very consistent. But when we look at the timings for the improper loop nesting, they're kind of erratic. So we go from 29 seconds to 124 seconds to 21 seconds. So this is a case where being able to get access to performance counters can give us a lot of insight. So what I did was I profiled this code using Gproff with the data access sampling configuration. And this gives me a lot of information on cache behavior. I'll pull up the spreadsheet a little bit later to show you the kind of information you get. And when I go into the function details section of the report, it shows that the number of cache misses is significantly higher for the improper loop nesting, but especially for that case of n equals 32,768. So again, the same table as the previous slide, except here we're looking at data cache misses instead of runtime. Now, number of cache misses, pretty consistent when I had the proper loop nesting. About 10,400, a little bit higher for the case of 32,768, and then a little over 10,000 when I bumped up to 32,769. With the improper loop nesting, you could see that its number of data cache misses are a lot higher. 195,000 for the first case, nearly 1 million for the second case, and a little over 100,000 for the third case. So what's happening here? Again, remember that the arrays that I'm working on are way too big to fit into cache. So I'm loading data into cache and I'm pushing it out as I need to put in as I need to access new array elements. So what's happening is we're having a lot of cache conflicts. An entire cache line is being loaded. But then, since I have the suboptimal loop nesting, I'm not, after I load that cache line, I'm not using all of the elements. I'm then accessing the next element in memory with a stride of 32,000 elements. Now, does anybody want to guess? Oh, I see another comment here. Oh, okay. Does anybody want to guess why the case of 32,768 is so terrible, even compared to problem size just slightly smaller or slightly larger for when we have the improper loop nesting? Okay, see in the chat. Yes, Matthew pointed out the only factor is 2. Yes, we are. Our problem size is a large value of 2. In this case, 2 to the 15th. And if we go back and we look at the way cache is used again, how main memory is mapped to the cache, we're going to find that when we're doing stride with a large power of 2, we keep banging on the same cache line. So we're using what we call a set associative cache, which means that each piece of memory can map to multiple locations in the cache. But if we're accessing with a stride large power 2, we're just pounding on those same cache lines over and over and over, and that's going to give us terrible performance. Oh, I realized that I actually left one slide out of here, but I don't think we missed anything important. Basically, where I took this data on the cache misses and the runtimes, and I normalized them to the runtime for the middle case for n equals 32,768. So with that, I'm pretty much done. But we have some more material that I could cover if you like on performance tuning and optimization. But I put together a bunch of exercises that you can do on your own. So for Gproff, I'm going to say run the Gproff example. You'll see a file called intro.f in the time-based sampling directory, and just convince yourself that you understand the output. Modify those functions f1 and f2 in intro.f to use sine, cosine, and log functions instead of square roots. How does this affect what you see in the Gproff output? You're going to see some lines that look a little mysterious. I'm going to say Google SVML when you get to that part. Note that trig functions, log functions are very expensive compared to multiplication, addition, and even relative to square roots and divisions. So they can lead to longer runtime, so you might want to adjust your problem size down a little bit. And for your convenience, I already have commented lines in the file that you can uncomment so that you can use the sine and cosine functions. Another exercise you could do with Gproff is break your intro.f into multiple files and rerun Gproff. And try to figure out, what does this tell you about the compiler's inlining capabilities? And there are two ways you could do this. One is to break intro.f into two files. I'm going to say a main.f, and then maybe a library file that contains sub1, sub2, f1, and f2. And then go further and break it down to three files. Main.f, maybe subs.f that contains the two subroutines, sub1 and sub2, and then funcs.f that has f1 and f2. And then also explore other compilers. In this case, the AMD optimizing compiler collection Flang, or the GCC G-Fortran. And try to figure out what they're doing in terms of inlining and other optimizations. And then self-paced exercises for Gproff. Unfortunately, we do, as I mentioned earlier, we don't have Gproff available for general use on the system. In fact, we just had Gproff installed on one node earlier this week so that I could experiment and put together this tutorial. Hopefully we're going to have it there soon, especially now that we've worked through the issues of the appropriate paranoid levels. But one thing you can do is to take a look at the AMD Gproff user guide. It's a little overwhelming. It's about 140 pages long. It actually reads quicker than you might expect, and there are certain sections that you could skip. Once Gproff is installed on Expanse, profile intro.f using the time-based profiling like we just did. Profiling the matrix addition problem using time-based and data access profiling. Look at what happens when you emit the -G flag on Gproff output. And then maybe go a little bit deeper into that matrix addition problem. Do you see the same behavior for other powers of 2? Let's say we go to n equals 16,384 or 8192, or to dimensions that contain large powers of 2. So for example, what if we try 2 to the 13th times 3 and see if see what the impact is on performance? And then also look at Gproff output and see if you get any insights from things like the cache misses. And with that, I am pretty much done with this section of the tutorial. If we have a little bit of time, I can get a little bit into performance tuning and optimization. Otherwise, I could answer questions and maybe show you some of the Gproff output. Okay, any questions, or was that just like way too much for this late into a Friday afternoon?
I'm suspecting the latter, Bob. There are some messages down here, some people with questions. Thank yous.
Oh, thank you, thank you.
I have a general question. You didn't talk, and we briefly addressed the AMD EPYC architecture with its quadrant of CPU of the CPUs and the cores. Do you expect to see some even stranger profiles in the Gprofile when you hit or miss that complex layout? Will we see like things get even more awkward when we have cache mismatches? Not evenly distributed across the different layout. What are they called, the CCDs?
Yes, I think what you're going to see. So the demo that I did here, but what was just for a serial code. We're just running on one core, so we don't run into that. But but when we start running MPI applications or threaded applications on a node, and we don't properly pin the threads or the processes to the cores, then you are going to see some big performance hits. In fact, we ran into that when we were doing a reliability testing on the large memory nodes. Yeah, so that will be interesting. And in fact, I think Uprof is going to be useful not only to the end users, but to our staff to try to track down some performance issues.
Definitely the cache optimization part of your talk was really, really interesting. And for you new users, you may not get to a point where you need to look at that, but it's really important to be aware of it and not afraid of it. Because sometimes, at the beginning when you're first running code, you're not at the point where you're even able to optimize, you're just starting to get it running. But this kind of awareness is really important down the road.
Yeah.
So
Oh, and
thanks
Mary,
for bringing that in.
And let me just add from slides 40 onwards, I have an abbreviated version of my performance optimization talk where I get into more cache optimization, loop level transformations, and so on. So if you're interested, scroll through it, take a look at that.
You want to give us a 10-minute blast through? Kind of just give. If you don't want to do that, you're free to go. We'll see you guys next week. We're looking ahead to a break, and in the next session we'll be doing some cloud computing and other interesting things. But if you're ready to go, go ahead. But Bob, I'd love to see you do a quick guide through, because that'll be part of our record.
Okay. All right. So actually, let me look at the chat here real quick. Do I have experience with cache grind? And what do you think about it? I haven't used cache grind. I would, in fact, I'm going to click on this so that I know to read about it later. And then Yogesh asked, okay, can these tools help us decide what is the good size of cache in main memory? Let me think. So I would say you don't have control. You don't have control over the cache in the main memory. But basically, you get what we offer. But it might help you decide what is the appropriate problem size to run. So if I go back to I'm just going to go back and look at my slides, the timings. You might find, so let's say for some reason that I was stuck with having to do that improper loop nesting, that there were some other operations in those loops that required that they be ordered in that way. Based on the profiling that I did, I might say, I'm going to be better off using a slightly different problem size. Or even if I really did need a 2 to the 15th by 2 to the 15th array, I might want to pad my data structure and store it in a 2 to the 15 plus 1 by 2 to the 15 plus 1 array. So yeah, so it can I'm going to say it could help inform what problem sizes you would want to run given the hardware you have available. And you know what? I'm just going to go ahead. I'm going to share my screen, show you what the output from Uprof looks like. So this is the output for, and this is all available in the CSV files in the GitHub repo. We see a breakdown. This is for the time-based profiling. I'll highlight this here. This is what we call the hot function section. So you can see which routines are counting for the most time. A little more informative if I go to the case with where I didn't have any inlining. You see it broken down by F1, F2, and so on. And let me open another. Let me unshare here. And here's an example of the output for the matrix addition problem where I did data access profiling. And in particular, you're going to be interested in, say the hot function section, and looking at things like like DC misses. These are the number of data cache misses. And if you want to get a little bit deeper into the memory profiling, that things like TLB, translation, look aside buffer misses. But it's really DC misses, which is going to be the key information that you're going to access. And Mary, regarding the optimization tutorial, I think what I'm going to do is I'm just going to go through real fast and not actually try to teach anything, because I think we're all a little tired this late on a Friday. But just to give a brief overview of what's in there. Does it sound good?
That sounds great. A glide through.
A glide through, yes. So everybody feel free to turn off your brains. I know I'm going to be turning off mine in about 10 more minutes after a really busy week. So don't worry about trying to absorb anything. So one of the tutorials that I've been leading at our summer institutes and other workshops for quite a few years now is on performance optimization. And there's an abbreviated version of that tutorial on slides 40 onward, where we talk a little bit about why you want to optimize your code, limitations of going parallel, implications for energy usage, some guidelines for optimizing your software, some ideas of how much effort you should put into optimizing software. So I'm fortunate that I love this stuff. I love working on software and tinkering on code. And I actually get paid to do it, or not so much anymore now. I've become, as my director likes to say, I've become a manager who manages other managers. So I spend most of my time working on spreadsheets and reports. But I still do get to dabble with this every now and then. But think about how much time you want to spend on this, because if you're an application scientist, all the time that you spend profiling and optimizing code is time that you're not doing your research. So think about whether or not this is really going to help you get your research done quicker, or if you're working on code that's widely used. Think of the impact that it might have on the community. Already talked about profiling. Cover compiler options. It's really neat if you get a chance to experiment with different compilers, with the Intel and the AMD and the GNU compilers, to see the kind of optimizations that they automatically do. I have a placeholder here for these were slides that were moved into the first part of the talk. And an interesting exercise showing that some compilers will actually take your bad code and repair it. So this is a case where the Intel compiler, when we fed it the improperly nested code with the improperly nested loops, the compiler was smart enough to recognize that was badly written code and rearranged it. You can see this, for example, on these bottom two lines here. But the AMD compilers, the AOCC Flang compiler, wasn't smart enough to do that. So kind of the takeaway is, try to write good code from the get-go. Compiler will sometimes help you, but sometimes it won't. And then after that, I get into a lot of different loop level optimizations. Ways that you could speed up your code by fusing loops together, or splitting them apart, or taking invariants from inside of a loop, pre-calculate and moving them outside. Go into an example from a real life code that I worked on with the USGS and the San Diego Zoo that was used for tracking California condors. So some more advanced loop level optimizations. And then, a few more cases from my experiences optimizing code. This was a collaboration that I had with NCAR in Boulder, Colorado. We're able to improve the performance of a global climate weather code. And then a little bit into something called force reductions, where you can look for opportunities to replace expensive operations with less expensive ones. Opportunity to go back and use your high school trigonometry. Talk a little bit about inner procedural optimization, where you can take a high level of the code and have a really big impact on performance. Revisiting that flow cytometry example I talked about in the beginning, and kind of wrap things up. So if you're interested, after your brain's recovered a little bit from a busy week, maybe take a look at those and get some ideas for how you can further optimize your code. And then if you have any questions, I am happy to answer them. Let me just put my email into the chat. So if you have any questions about the presentation today or possibly optimizing your own code, feel free to get in touch. And Mary, I think with that, we will just wrap up.
That sounds good. I'll go ahead and stop the recording. Thanks everybody for attending. We'll see you next week.
Great. Thank you, everybody.